Here's an idea for you. Every maker should have these three machines. They are a 3D printer, a CNC router, and a laser cutter. Of course, we aren't going to buy one, although it'll probably be much cheaper in the long run and save blood, sweat, tears, and maybe cash as well, because where's the fun in that? Instead, we're going to build ourselves from scratch. So here are some basic specs if you're hoping to get a rough idea of what this project will be about. So let's move on to the cost. So we are going to go over the projected and actual cost of this machine, and I originally intended to spend no more than $500 on this machine, and the rough gauge of the breakdown of costs were as follows. So for the laser parts, I was intending to spend about $200. For the frame, it's going to spend about another $200. Electronics, power supply, $50. Miscellaneous parts, 3D printed parts, etc., another $50. So all in all, this is how much I spent thus far. This does not include miscellaneous items such as cooling and ventilation, but you get a rough idea. For the frame, I've spent about $232. For the laser, tube and accessories, $192. For the electronics, $49. And for miscellaneous stuff like lead screws, smooth rods, printed parts, etc., $68, and this brings the grand total to about $541. Most people would think that cost would be a major driving factor for a DIY build, and they aren't wrong. Even at $600, our laser cutter still stacks up pretty nicely compared to our nearest contender on good old AliExpress, which costs about $300 plus USD, and that's not even considering the sometimes almost the same cost as the product shipping fee. Closer to home, Lion's Forge, which is a local laser manufacturing company, also creates laser cutters, but the price is sometimes quite chilling. It doesn't go to say that local/overseas plug-and-play lasers are no good. In some sense, you are paying for the reliability and troubleshooting that has already been done beforehand. At this juncture, I also like to point out that DIY isn't a silver bullet by any means. As I'm recording this right now, I should have invested over more than 100 hours in designing, sourcing and building this laser cutter, and I'm still grappling with some stupid issues which I would probably have not faced if I had simply bought a laser cutter off the shelf. But of course, there are other benefits, and don't get this wrong, these benefits are quite huge. For instance, you have absolute unchallenged say over the size of your laser cutter, which means that you can make it as big as you please. And trust me, for the amount of time you're going to spend on this project, you might as well make it as big as you possibly can. Taking a look at our contenders, we see that the build volume is pretty limited, but for us, we do have a whopping 1.2 by 0.5 meters, limited only by the size of our table. Lastly, there isn't as a joy as unspeakable and as pronounced as when you see your handmade creations come to life. Okay, maybe not, but you get the idea. Speaking of size, now it's time to discuss a bit about the design process. As mentioned, all parametric design was done in Fusion 360, and as you can see, it was not very well designed. For starters, what initially started out as an adjustable parametric design via parameters essentially broke down due to mistakes in the referencing and whatnot. I still do want to create a calculator that allows anyone to get lengths of element and profile for a custom size laser cutter though. Moreover, the entire design was done before I learned about the wonders of components, so literally everything is a body, and any components you see here were made retrospectively. As with all designs, we started with the table. In this case, it was a 1.4 by 0.7 meter table that is sitting on my workshop. While designing this laser cutter, I wanted to maximize the build area, because bigger is better, while ensuring that I could properly isolate the electronics from the cutting chamber. As such, I designed the cutter first, trying to squeeze the X and Y steppers into the frame, and then basically designed everything up from there. To keep costs down, I ran with the cheap and cheerful V-slots rather than linear rails because they are cheaper. I also went for a belt design for the X and Y axes, because once again, belt is cheaper than lead screw. To position the steppers, I thought long and hard about my various options. On one hand, I could emulate something like the CR10 for that matter, or the Ender, with the stepper motor mounted next to the 2040 aluminium V-slot, like this, but that would mean I would have to put an idler roller on the end of the V-slot, which means it would not be able to line up nice and square with the wall. Now, given that we couldn't afford an open concept frame for safety, I foresaw that it would be a pain trying to secure all the linear rails without having them attached to the side walls in some way or another. This was what led me to choose the method which I eventually settled on, having the steppers mount on top of the V-slots and drive a belt loop that literally also sits on top of the V-slot. Another mega consideration was mirror alignment. This was something with which I experienced an immense amount of luck with, which I will address in a later video on rants. However, since I chose to put the x-axis on top of the y-axis and position the steppers on top of the V-slots. This really helped me to provide an elevated platform from which I could place my mirrors, and that was really helpful. The Z-axis is essentially the most clunky of the three, as it has to lift a massive bed which firstly weighs a ton thanks to the sheer amount of aluminum profile required to maintain and support the large bed, plus the soon-to-be honeycomb aluminum. The Z-axis was originally intended to be powered by a single stepper motor driving a massive belt, parameter 3.8 meters, that would spin each of these 36 tooth pulleys. For that role, a 1 amp stepper would definitely be needed. However, my ambitious plans for a mega loop were soon foiled by the fact that nobody sells such a mega GT2 pulley loop, as I would need about 3.8 meters to be safe. And trying to stitch a belt row into a closed loop is virtually impossible according to forums. Nonetheless, I decided to change my plan to include 2 steppers operating each of sides of the bed with 2 individual end stops in marlin for the Z-axis, so assuming that Z-axis should be a thing, right Marlin? Speaking of end stops, the Y end stops are nicely integrated into the stepper mount with 3D printed offsets triggering them. Initial trials saw some minor hiccups, which I'll elaborate during my rant video, but let's just say the basic design seems to have held up relatively well. The belt system seems to be holding up, dual Y end stops work well, and the system overall seems to be working. Yay! In the next video, I will go over the physical build process and some things I learned along the way, as well as to discuss the most interesting yet challenging part of this build, the aluminium exterior. I think that is all for the first video. If you have any questions, feel free to leave them in the comment section below. As always, keep designing and making stuff, and I'll see you in the next one.